explore situations like this. So what you are seeing there is a circuit where you have a light bulb connected by a series of wires to another light bulb, and then you have a battery. Now, I have already introduced the idea of the positive and negative terminal of a battery. In the first lab, you guys have seen that you can plug a power supply using banana or alligator cables. And you can use that to power a small circuit. In this week, you're going to be using a light bulb and a resistor, and you're going to connect it using a switch and a battery to close a circuit to analyze what we know as Ohm's law. Ohm's law is basically the relationship between current, voltage, and resistance. What do you think is resistance? In mechanics, you went over the idea of friction. If you have a mass and there is friction and you exert a force, eventually because of friction, the mass will slow down because of the force of friction. The idea with resistance, right, is to have some sort of resistance, yeah, to the flow of current. So if you have a cable, a copper cable, and you introduce resistance or you place resistors in a circuit, you can calibrate, you can slow down the motion of the electrons. You can basically reduce the amount of current by adding more resistance. That should give you an idea of the relationship between voltage, which by the way, voltage is now what we call electric potential, the voltage of a battery, volts. Resistance, which we measure it in ohms, and current, which is our new definition today, which is given there. Current or electric current is defined as the amount of charge flowing in a given wire or circuit by the amount of time. Is the rate of change of current per unit time. Delta Q over delta T. Coulombs per second. That is the ampere. All right. So, to analyze, to introduce current, we first have to introduce the idea of a battery. Now, electric potential introduced the idea of volts. And then we use that to define the electric potential energy. So let's use that to analyze what a battery is. Basically, a battery, by using chemical reactions, will provide a potential difference between the terminals. 1.5 volts, 3 volts, 6 volts. It depends on the size of the battery. The higher the battery, the more charge it can hold. Right? Q equals to CV. So we still use that equation. But now we're going to forget about charge. We're going to focus on the voltage. If you have a battery with certain voltage, you are basically introducing electric energy in the circuit, which allows current to flow. It's like what you see in the picture there. If you have some sort of potential difference between the initial position where you are serving water to position B here, there is a potential difference, right? Because of the slope. So the current can flow just like water. That's why in some textbooks, they use the analogy of water flow to current flow. And that's going to be useful when we start talking about junctions, nodes, right? Here, you are seeing the you are seeing how we can define a circuit. You have the battery here, you have the switch, how we label it, and you have here the light bulb, which might be your resistance, We label it with R. The battery, normally we label it with V. Normally, not always. Why? Because in the next few slides, you're gonna see that we're gonna introduce the concept of E. What is this E? Well, in theory, that's the nominal value of a battery. When you buy a battery in Radio Shack, I mean, Amazon, Radio Shack, I don't think it exists anymore, unfortunately. But when you used to buy batteries in stores like Radio Shack, right? They will give you the value of the battery, right? 1.5, 9 volts, maybe, depending on the size, depending on what you need it. But that's the theoretical value of the battery. If you use a voltmeter, especially if the battery is connected into a circuit, like here, you may read 8.8 volts, not really 9 volts. So where did the 0.2 volts went? Well, that's when we introduce the idea of electromotive force. When the battery is disconnected from any circuit, we can say that between the terminals, we are measuring the EMF. The EMF is basically the amount of voltage required to move a charge from point A to point B. In other words, is related to the work done to move a charge from one potential to another potential. That should sound familiar because that was our definition of electric potential. Basically, the amount of work per unit charge. But that's if the battery is unplugged. When you plug the battery into a circuit, you obtain the voltage. So what is the relationship? Well, it's not in the slides. It might be in the textbook. But the relationship between EMF and voltage is this. V equals to the EMF minus IR. All right. The reason they don't give you that equation there yet is because the IR is what we are going to define as Ohm's law. And let's go ahead a little bit. This R, if I were to draw a battery, in real life, a battery is not like this, right? It's a device. I mean, you have seen power supplies in the lab. Those big green thingies. A power supply or a battery, they have inside an internal resistance R. The internal resistance is the reason why the voltage is different than the theoretical value or the EMF. Now, depending on the specification of the power supply or the battery, normally the value of little r is very small, so small that it can be negligible. That's why I said, if a battery is of 9 volts and use a voltmeter and you read 8.8 volts, the 0.2 volts or 8.9 volts, that is because of this. But that's still very small. And there are some cases where the readings may be 8.95, 8.96 volts. So the difference is basically negligible, right? But that's the reason why you have, a difference between the voltage and the EMF. And I'm pointing this out because when we do electromagnetism or magnetic fields and induction, we're gonna go back to the idea of an EMF, all right? But for now, we're just gonna keep it as the voltage V. Okay, so that's to introduce a few new variables, the current R, the resistance R, and the value of E. Now let's talk about direction of current. You are gonna notice that when I draw the current direction in problems, I'm going to use the green direction that you see over there. So from positive to negative. However, you probably already know that there is a problem with that. When the idea of current was introduced and discovered, it was believed that the current was due to the motion of positive carriers, aka protons. However, after we have been deciphering the atom, after understanding the composition of the atom, more specifically the nucleus of the atom, and realizing that protons are heavier than electrons. And as I explained the first day of class, you actually have transfer of electrons, right? Then we realize that current is due to the flow of electrons. So it doesn't make sense that electrons will leave the positive plate or the positive terminal of a battery, right? It makes more sense that current is actually on the red direction. However, the convention was built based on the green direction. So we just use that. Does that mean that we are wrong and everything we've done so far in science is wrong? No. You're going to see maybe even tomorrow that especially digital ammeters, they read negative currents. So what's the meaning of a negative current? Well, basically means that you are reading current in the opposite direction. The value of the current is correct. You just have to change the direction of the wires. We call that in the lab changing the polarity of the cables. So there is not really a problem in terms of the value of the current. It's just a direction of it. Do we have to be careful? Sometimes in electrical engineering, you have to be careful with that, yes. But in basic circuitry, not really. You can just change the poles when you are plugging into the ammeter or the battery, and that fixes the problem, which is why we can just keep the convention for the direction of current. All right, so that is with the direction. And then let's talk about what's really happening when current is flowing in a cable. Whenever you have current flowing in a conductor, right, what we actually see is there in front of you. We don't see electrons flowing straight without any sort of bouncing, because there are so many electrons flowing per unit volume in a cable. And many of the cables that we see in real life are so thin, right, that electrons are gonna bounce randomly. So the motion of electrons, because of these collisions or bouncing, is actually very small, or sorry, very slow. So electrons can take a very long time. And we're gonna do a problem tomorrow at the beginning of class for sure, because that's a long problem, to show you how long it takes for an electron to travel in a high power cable. You know those cables that we have outside that we use to provide electricity in cities, right? High transmission cables. They have large amounts of current. Therefore, they should have a large amount of charge flowing in them. But because there is so much charge, there are so many electrons that they're going to bounce so much that it can take years for an electron, for a single electron to travel from one end to another. So then how come electric signal travels so quickly? Because electric signal is governed by the electric field. When I introduced the idea of an electric field, I said that as soon as you create, let's use that word. As long as you have an electric potential between a parallel plate, you have an electric field in between the plates. It's the same with an electric signal. The electric signal is governed by the electric field. That's why the electric signal travels much more quickly. All right. Okay, so let's actually show you the equation for this. So what is the equation for electric current? That's basically the microscopic definition of current. So if you have a cable, I'm going to zoom in like in the textbook. And you have a surface area which can be approximated to a circle. Area A, some distance delta X. So that multiplied with the volume. And then you have the electrons or the carriers moving from left to right. The electrons move very slowly with what we know as a drift velocity. So these electrons here are moving with this VV, drift velocity. Now, the amount of current depends on the density of carriers. It's the amount of carriers per unit volume. Now, that depends on the type of cable. Aluminum, gold, copper, they all have different densities and different molar masses. So you can use both to find the density of carriers. So then we can define the current flowing as the density of carriers N multiplied by the drift velocity multiplied by the area multiplied by the charge of the electron, the magnitude of it. This is the microscopic definition of current. Where this N is the density of carriers. This is the drift velocity, A is the area, and that's the charge. So there you are, okay? When we need this equation tomorrow to do a very similar problem that is in the textbook, and it will show you how slowly electrons move. So is that the only definition of current? Not really. The more simple definition is when we start using the idea of conductivity or resistivity, basically bringing Ohm's law into the mix. All right. So let's share this again. So what is Ohm's law? Ohm's law is not really a universal law. Why? Because a lot of materials are what we know as non-ohmic materials. They don't follow Ohm's law. Tomorrow, before class, we're going to be given two different materials, a resistor and a light bulb. A resistor, which is ohmic, you will find that it will follow this. if you plot the voltage supply to the resistor as a function of current in amperes, and this is voltage in volts. If you plot these two in the X and Y axis, for an ohmic material, you're gonna find this. So what do we see here? We see a linear trend. You see this? As the voltage increases, the current increases. That means that the rate of change is constant. And what is the rate of change? That is your value of R. And what's R? That's the resistance. The resistance is defined as the change of voltage, or V divided by, so V over I. That's Ohm's law. Right here, R equals to V over I. Voltage over ampere, that will give you the units of ohms. So 1 R, the units are in, let's put it here, the units of R are in ohms, which are equivalent to the horseshoe, like that. That's Ohm's law. That's what you will find. So what about a non-ohmic material? A material that doesn't follow Ohm's law. What you will see, for example, with a carbon resistor or a light bulb, is this. So if you were to plot let's suppose you have a non-ohmic device, resistor. If you were to plot V versus I, you will start seeing something that looks like Ohm's law, but then you start seeing this. Right? So it's not really linear. It's more like a power sort of relationship. So it's not linear. So that doesn't follow. So that's why it's not really a law. It's not really a universal law. It's convenient only for certain devices. All right.